Hello, I'm Paul Henderson from IST Austria, and I'm going to speak about this work with Wachit Simonaki and Christoph Lampert on leveraging 2D data to generate textured 3D meshes. The traditional approach to building a generative model over textured 3D shapes would be to create a large dataset of them, then to use that dataset to train a GAN or a VAE. However, 3D shapes with detailed texture are expensive data to obtain. Instead, we propose to learn our generative model from unstructured collections of images. In particular, we don't require multiple views per instance, we don't require any 3D annotations, and we don't require ground truth segmentation masks. Our overall approach is to force our model to explain its training images, each in terms of a textured 3D foreground object rendered over a 2D background. Importantly, it must do so while forcing those shapes and textures to be encoded in a low-dimensional latent space, which allows sampling. To implement this idea, we design a probabilistic generative model of images, which incorporates the foreground object's shape and texture as latent variables. It first samples a mesh by drawing Gaussian shape and texture embeddings, then passing these through decoder networks to give vertex locations and face colors. We then model the process of forming an image showing the resulting mesh. To do this, our model samples a Gaussian embedding for the background and decodes that to pixels using a decoder network that has low spatial frequency to discourage modeling parts of the foreground object. Then it places the mesh in front of a perspective camera and differentiably renders it over the background. Finally, we add Gaussian noise so that the likelihood is well defined. We train this model like a variational autoencoder. That is, we add an encoder CNN that predicts the latent variables which explain a given image. Then we optimize the encoder and decoders together end to end. We maximize a variational bound on the training data likelihood. This loss requires that the rendered image match the original and that the latent variables match the Gaussian priors we impose on them. We train the model in two different settings. The first is with ground truth segmentation masks. In this case, we have an additional loss term that encourages the rendered silhouette to match the ground truth mask. The second is without masks, so we have only the pixels to learn from. Outputting meshes from a neural network which has been trained for pixel or silhouette reconstruction alone typically results in many intersecting faces which aren't easily visible in the reconstructed image. This is difficult to avoid by local surface regularization, like Laplacian regularization, because for spiky, angular objects such as chairs and aeroplanes, it's impossible to design a local surface regularizer that can distinguish good from bad geometry. We therefore propose a novel method to ensure that the meshes produced by our decoder cannot contain any intersecting faces. We do this by parameterizing meshes as a sequence of deformations applied to some non-intersecting base shape. During each deformation step, faces push one another out of the way instead of colliding. In the example on the slide, the decoder outputs a global direction of motion and a distance for each vertex, shown by the blue arrows. When applying this movement, the red faces get pushed out of the way. Mathematically, this can be set up as a linear programming problem, and we solve it by incorporating a standard LP solver inside our network in each training iteration. We also show how to propagate gradients back through this process. We evaluate our method on 4 classes of synthetic images and 2 classes of natural images. Our first experiments use renderings of ShapeNet meshes, though note that the model never sees these meshes, only the renderings. Here we see the qualitative results on cars, chairs, aeroplanes, and sofas, which show that the model produces easily recognizable and diverse samples for every class. We also test on 2 natural image classes, birds from the CUB dataset and cars from the Brno-Com speed dataset. Again, our model generates plausible and diverse samples for both classes. Thank you for listening.